乡的波霜，窗前的月光，都照亮心底某个地方。有人用思念两段粗石行，流淌过1000年，恋恋难忘。你有绿树红墙，替我遮风霜，也有草场白云白，吹到长城长。天水煮小巷，早上老火汤，再加3分时光，坐在门前慢慢尝。人间烟火山河浩荡，清风过大江，水路弯弯连海浪，两岸千里的花香。你爱的人啊，记得你最好模样，你是大宝的忠贞，是心之所向。时代滔滔向前，温柔而勇往，留不忘。That's this. It's always that time I forget to turn on the mic. Hello, Simon. Last time in last stream we did breadth first search, and so this time we are working towards the next treat algorithm, which is depth first search. I don't know if it's just me, but like for me, I think depth first search is harder than breadth first, because it involves recursions. But I think this is generally more harder than the previous version. I mean the breadth first. Let's start with the question. Path with the given sequence. Given a binary tree and a number sequence, find the sequence is present as root to leaf path in the given tree. But didn't I do this already? Already did this. So this basically, you look at the index and you look at each. Within each sequence, within each node, we look at the... Oh shit. Oh shit, my mouse ran out of battery. Need to plug in. Hello, Mabuchi-san. Happy Friday. For someone that's unemployed, there's no Friday. We always... I'm always working. So whenever we get into node, because we know the index, because every time we traverse to the next node, because this is depth first search, so we go down to the leaf first before moving back up. So each time we go down, we know the index is gonna increase by 1. So the basic is basically whenever we go down by 1, we look at the next index of the sequence and look at the node compared to the value of the node. If they're not the same, then it's false. Then if they're the same, then we keep going down to the next until we hit the leaf node. And then the last sequence is equal to the leaf node, and there is no more like Because it's a leaf node, so there's no more left and right. So that means we found a sequence. And that's the basic of this. I already did that. So next. Next. Count path for a sum. Given a binary tree and a number s, find all the paths in the tree such that the sum of all node value of each tree equal to s. Please note that the path can start or end at any node, but all paths must follow direction from parent to children. Okay. So we are giving a sum, and we want to find all the path that equals to a sum. Okay. So I'm gonna create a new function called find path, and we want to pass a rule. We want to pass s, and we also want to pass whenever we find a sum, we want to continue the algorithm until we finish. So we only do that until. So we need to have a value to store all the paths that we found. Right, so all paths, and then current path. So let all path equal to, we're just gonna use an array to store the values, and current path also use array. Okay, so whenever we traverse, we want to find path again, pass rule s. In this case, we want to have the nodes root.left minus s, because we want to remove s. Actually, no, it should be s minus root left. So each time we go down to the next node, we want to reduce the sum, and then also passing all path and current path. And for the current path, we do current path dot push root dot value, and then we also do that for the right side as well. Find path roots s minus root dot right side, and all path and current path. Right, so let's take care of the edge case, because this is gonna keep going down this is a recursion, infinite recursion, so we need a way to stop this recursion. So if the root is null, that will just return. And then what we're also looking for is if the value we're looking for to the path that we're looking for is when we hit the leaf node, which means the remainder of the sum is gonna equal to the value of the leaf node. Then we also want to make sure that it's a leaf node, so we're gonna do root.left is equal to null, and root.right is equal to null. So this makes sure that we are the leaf node, and the last value is equal to the last number that we need to complete the sum. So if we do that, then if we found that, then that means we found an all path. So we do a we do all paths, dot push, current path. And then we finish this and we return. Actually, we don't need to return because this is eventually gonna hit a node and return that. So we just gonna call this find path and then pass in the roots, the sum, or path, and the current path. I think that should be it. Run this. Maximum stack, because okay, because in this case we need a way to stop this. If it hits the root, then in return equal to next, it's a root and return. How do I stop this? If we find an all path, then we return. If we hit a no, then we return. Oh, return 0, because this is return 0. We want to return all path. Maximum call stack. Find path, find path. When we hit the leaf node, then we push the current path. And we return. When we hit the node, we return. Do you vibe code? What do you mean vibe code? Coding by the vibe? Do I? No, this is not an our return. This line path. How do I stop this from running? Cause I think the current problem is. So we do this. Find path. Find path is gonna push current path. Current path is gonna push this. And then we do find path for the left node. And then push this to current path. And we do left for this. Right. And then this left is gonna hit this. Assuming it's the same, you push the current path and we return. We return back to the previous find path. It's gonna do a find path to the right side. So because the right side, there's no right side, it's no. Return no. So we return. And then this is gonna return back to the top. The top now is gonna look for the right side. Right side keep going down. This should stop. Why is it not stopping? Maximum call stack. Okay, let's see how they stop this. They do a current path or pop. Remove the current node from the path to the backtrack. Oh, because I'm storing too many current paths. Is that the reason? Current path? Dot pop. Run again. Do maximum size. current path dot push. I don't think this matters, but so instead of pushing, we're gonna do this instead. The val, then the val. I run this again. Maximum call stack. So they do a recursion count path, you passing in current path. Current node. If the node is 0, then you return 0. Okay, current path, you push the current path to there. And path count is 0, path sum is 0. For let this less than. Oh, so they are doing a they're doing a for loop within that will calculate the path, because all they're doing is they're pushing the current path. Oh, they want to they just want to count. Oh, I see. But still the same. I think you don't need to do that. Like, cause if you do a recursion, I just minus the sum. Then you will. Then you eventually arrive the same thing. And then they do current path count. Increment path count. And then you pop the current path. Oh, okay. But that's still the same. So let's see. Current path dot push rule dot val, and then we push current path. This doesn't matter, so this is return or path of length. But we need to stop the recursion. So problem number 1 is current path gets updated. Doing this, we push to the current path value. So if I console log current path, it's gonna be massive. Keep increasing. Run this. Nothing. Wait, nothing? Maximum core size exceeded. Why? Return 0? I don't think that matters. Return 0. Run. So this find path root dot left. This find path. And then this find path root dot left. return. And then this return back to the top. We do this find path. You keep doing this find path and return to the top. And this path is finished. After returning to top is finished. So next iteration will be the first one that initiates this value. So this path is finished. We go to the next one. And then it returns. Why is it like this? So one never end. What the fuck am I doing? Root the left, root the right. So the find path is always gonna look for roots, and then look roots, go to next find path. You're gonna look for root again. If next find path and root again. Oh, that was dumb. No wonder why. That's big. Run again. Okay, so now we just do a current path up top. Run again. Let's see, console.log current path. I believe this is, if I remove this, is gonna keep increasing. So the path, yeah. What we need to look for is, for the path to be. So by the time we hit this, is this gonna be at the end of recursion? So we want the path to be 3, length of 3, because this is a. What example did it give? 10169. Doesn't work. Okay, we don't know what this is, but I think this is a depth of 3, which means this value should be 3. So by the end, we pop this. So this means we found a current path. So don't log all path. But this is not triggering. Oh, I think I see why. Because I'm doing this, I'm doing both. If I'm doing both, that means both S is gonna remain getting deducted. Also, that's why they did it that way. That's why they have a for loop to calculate that every time. Because if I'm... So normally in a recursion, if you do an OR, so that means this is gonna run down, right? If you return this OR, and you're only looking for one value instead of the count, then this S is gonna stay. Okay. Okay. In that case, which is near index? Index is equal to 0. Loads return 0. Current path push is fine. Or, and then each time we go down, we increment index. Oh, we don't need to increment here. So in this case, if we do a fine path, we need to push S. We need to push index. We need to push S, then index. So in this case, we'll push index plus 1. Index plus 1. If index is equal to root dot length, not the root dot length. Oh, I don't need index. Still need current path. Current path is equal to nothing. Current path. So current path push this. Let I equal to 0. I less than current path of length. I plus first. Let sum equal to 0. Sum plus minus. Current path dot I. Current path index I. If sum is equal to... So we have a counter. We also need a counter. Let counter equal to 0. If size is equal to S, then we increment counter. At the end, we just return counter. So if we hit the roof, dot left is equal to null, and root dot right is equal to null. Then we do this calculation. Run again. And now read property on define reading push. Oh, current path. All path is not defined. All path. Oh, because I'm not doing this. One again. Cannot read property undefined within length. As I'm trying to... Okay, so each recursion counter is gonna set to 0, which we don't want that. Return counter, and we'll return this. 0, okay. At least there's something going on. So if I put counter outside, and we're just passing the counter itself being here, like passing counter here, passing counter here. One again. Counter is not defined. Oh, because I'm not counter. Wait, why am I passing 0? So passing counter, passing counter. One again. Still 0. What's the point of doing Leetcode with LLM being able to solve both of them? That is very true. Machine learnings, I mean, like generative AIs cannot solve for, like, you just take the question, you take a picture of this question, you send it to ChatGPT, they're gonna give you the most optimal answer. That is correct. However, hiring companies, they still do this, and then they don't want you to use ChatGPT. That's the problem. Like, you cannot go to an interview and they say, oh, let me use ChatGPT. Oh, because I'm passing 0. Enter. One again. Are you looking for a coding job? Yes, I am. I am actively interviewing right now. I don't even do return 0 here. Any luck? No luck so far. Maybe I am getting interviews, so but no offer so far, I guess. I only started applying like last week. Yeah, the problem is like coding job is hard now. You guys probably heard the news. If you look at news, then you will heard like a lot of high tech companies doing layoffs since last year, and the amount of job openings. Well, so it's layoff plus the amount of new job openings is very low. So there's a very high competitions. So this pass the anti-array, return this. Current null is null, return 0. You push the path count, path sum. Let I is equal to the current path of length -1. I greater than I minus. Path sum is equal to this. If path sum is equal to this, you increase the path count. Yeah, that's what I'm doing. Path count is equal to path count. Oh, your return path count. So even though they are setting this to 0, you increment this. And then you run this again. Oh, you increment this and then you increment the count. And then you have a 0 here because you don't care about the last value. The last value count is gonna increment by 0. Yeah, for some reason recursions fucked up my brain. It really fucked up my brain. So I can do a counter here, let counter equal to 0. If these are no, then we do a sum and we increment the counter. We don't need to return here, because we're gonna increment counter from here. Down to plus minus. And this will return 0. And we return counter. Run again. Let counter equals 0. Identify because I have this here. Run again. Okay, now we are getting somewhere. Hold, there's no counter here. I don't want to pass counter here. Run again. Okay. So find path, we return the find path. Find path, we pass in current as empty. If it's no, we return 0, then we keep pushing this value. We have a counter. If we hit a leaf no, a leaf no is slide, both of them. Wait, hold on. Oh, I see. I was expecting the entire path to be equal to the sum, but according to these explanations, you don't need to have the whole path. You can have partial of the path be equal. Oh, so that's why. That's why I see. If we only want the current path to be equal. Oh, that's why they're doing reverse. Okay, I see. So you only want partial. Either the entire one or partial. Or is it partial? Please note that path can start or end at any node, but all paths must follow direction from parent to child. Top to bottom. If I move this up here, now we're getting more. Okay, drawing dark mode. Online drawing dark mode. Link to 1 0 1 1, I guess. No. Oh, 1 0 1. No, this is no. 6 5. So the counter should be 2 in this case. Why is it wrong then? Once we hit there, we calculate that thing. But if it can't be partial, we don't need to hit the rule now. If we can be partial, we don't need to hit the rule now. But how do we know the path? If I just keep calculating that, current path on length -1. I greater than or equal to 0. I minus. Now it becomes 1. Okay, if it must follow top down, which means we want the bottom value. We want to decrement from the bottom value. Right, this is a 2. This is also 2. So based on this current value above, current path. Based on this current path, the value should be 2. Right, increment counter. Once I hit the bottom. Oh, because this one hasn't hit the bottom. Oh. Is it? This one hasn't hit the bottom. If I calculate that every single time, it's gonna be high time capacity. So this is correct. Submit and also correct. But the problem is like this is computation more intense. Every time we go down, we look for this value. So if I don't pop here, see that's very computation. Wait, no, why is this still accepted? Counter equal to this find path. Counter equal to this find path. And then if we go up one more. Oh, because this is the current root. So if we go up one more, we'll kill the current root. We should... If we do 2 find paths, and then we pass in current path. So by the end of this current path, you have to... This goes down current path, you push a value. And we calculate this. After we calculate this, we go down. We push next value. Because there's no next value. If this, assuming this is a leaf node, right? This happens, and then we go down to the next one. If the previous one is a leaf node, that means this value we go down, it's gonna just directly return 0. So the push happened before gets returned. So that's why we can just pop. If we do a pop this, then it's popping this value. But assuming this is the leaf node, assuming if this is a leaf node, so this pushed value current path gets pushed, we do this. After we do this, we increment this. And then we go down again. We go down again, this is a node, so we turn 0. So this goes back, and this is passing the, let's say if the leaf is F3, so this will be F3, return 0, this still be F3, and then, oh, because this is the next leaf, so next leaf is gonna go back here, also return, this is F3 right now, so return 0, and then we pop that leaf, and then we end the third chain, we go down here. Oh, I see. Yeah, this fucks you up. This really fucks you up. Let's see. Suppose this is like this. Right, 1. So recursion is we have a leaf node, we go down. We look at left, right. Assuming this is like this. So this is like 3. We're looking for 2. We go down to 0. And then we're gonna compute. We're going to compute from bottom to up. And see if this... So S is 2. We compute, this is not S, so we keep going down. We go to the next node. And we compute again. S is 2. Right, so the current stack is 1, 0, 1. So S is 2 is correct, so we do a counter plus plus. Counter is no 1. And we keep going down because there's nothing, so return no. Return 0, then there's nothing changed. This also doesn't change because if this is no, this is 0. I mean, this if it's no, then we are not pushing any value in the first place. So this goes back to here, and we look at the right side. Look at right side, still no. So this doesn't get pushed. And then we go down to the next, and then next will be this value gets popped. After it gets popped, and we return the counter. Return the counter to the previous value. So next we go down to 3. So we push 3 to the value. We compute that value. It's not equal to 2. So we don't increase the counter. And 3 is gonna continue to look down. It's null, return 0, and this doesn't get pushed. We look at right side, it's null, pushes 0, and counter doesn't get increased. So now it goes back. It goes back here. Now we're at this step. So current path is like this. So we pop the current path. And we go back. And then after we pop the current path, we go back to here. We go back to here because we already did left and right. We already did left and right. Because left is here, right is here. So we already at this path again. And then 0 gets popped. And then we move on to the next, which is 1. So 1 push here, and we do the calculation. It's equal to 2, so we increment the counter. We look at left, we look at right. No, so nothing gets pushed. After that, after that 1 gets popped, we go back to here. We go back to here, which is this step again. Right, this step. And because we already look at left and right, so this 1 gets popped. And finally, the last, because we incremented counters by returning the counter. We just incremented counter plus each time we traverse. So counter is still at 2, so at the end we just return the counter. This gets and then this gets a return. Return back to this path, and this gets a return, so counter is at 2 now. Oh my god! So what they are doing different is like they have a path count. Path sum. Oh, they're doing the path sum. If path sum is greater than... Well, they're still calculating this every single time, so it's still the same. I don't need the path sum. I don't need to do it the same way they do. Because each time they do the recursion, there's a for loop happening. One thing we are repeating is each node traverse. We're looking at subpath that ends at the current node gives us the required sum. Let's see if we can improve this. God damn it! I was trying to do this in the first place. So current path sum equal to no value. Each time you move down, you increment current sum. I was doing this in the first place. If the map has they have a map. They are calculating the current sun. Current sun is the way. Current sun is each time you go down the recursion increment current sun. If current sun minus target sun. So if map has that value. Each time you do that, you increment current sun, then you push in the map. You map. Map the current path or +1. If map has this number, that means if you're going from bottom up, you have a path count, you increment path count there. Current path sun is getting increased every time. Map target parent path -1. So in this instance, they also have a map. Instead of recalculating every single one, you add the sum 1, 0. So 1 is 1. Go down to the next one. 2 is 1. And the counter minus current sum is equal to 0. I should know. Current sum minus target sum. If map.get if current sum minus target sum is 2, 1 minus 2 is -1. Map.get this, it shouldn't have a -1. So current path sum plus 1 at the end will be 2. Oh, because they already do this. They already do this. If they're equal, then just increment. If they have greater than, and you have a previous value that does that, then you increment as well. Cause this is a case where it's a sub. If the sub tree, if the subtree is equal to a target sum. This is if the entire tree, not entire tree, if from top to bottom is from the all the way to top from top to bottom before ending at the leaf is equal to the target sum. Then you comment this, and this case is from bottom to top, because we don't have to be always the from starting from the root node. So it could be the middle node to the next node is equal to from the root to the next, not from the root, from the middle to middle somewhere or to the end, if it's equal to the target sum. That means if that value minus, if the entire tree for the entire path minus the target sum is gonna be equal to the excluded sum. In this case, let's say we have another one here. So this part, so the total will be 3. Total minus target sum will be 2. That's equal to 1. So we already have 1 in the map. That means we can already increment this by 1. Okay, this is understandable. And then you just set each time you increment the current path sum, you either create a new value of 1 or you increment it by 1. At the end, after we pop this value, we're gonna take this out. Okay. There we go again. We have a current path. We also need a current sum. Not current sum. Current path. We need a map. Map is equal to new map. So this one, instead of pushing to the current path. Wait, do I push current path? Nah. So now it's current sum. Current sum. Instead of pushing the path, we do current sum plus minus root of value. Because if root is null, then return 0. And then we create a new map. New map is gonna maps dot set current sum current sum current sum, and we're looking at map dot get current sum. If map has a current sum, then we plus 1, otherwise we just 1. And the cases we're looking for if the current sum is equal to the we have a sum here. So if the current sum is equal to the sum, current sum equal to sum, then sum plus plus. But this shouldn't be called sum anymore. Counter. If current sum is equal to s, then we do counter plus plus. And now, if we're looking for partial, that means if current sum minus s, if the map has current sum minus s, then we also do a counter plus plus. So now counter is equal to find path. This we're gonna pass in current sum, we're also gonna pass in the map. Current sum and map. At the end, instead of popping the path, because before we were pushing the path, now we're adding the sum. So we just take out the new sum that we added at the end, which is map dot set current sum map dot get current sum. If there's a current sum, there's a current sum minus 1, and return the counter. Runt 6, that's a lot. Okay, current sum is equal to root of value. Yeah, we have a counter. Counter should be at the top. Well, counter and the current sum is all gonna increment by the root value. And then we set the current sum to be either the current sum or 1. To be either current sum plus 1 or 1. If current sum is equal to s, then we counter, increment counter. If map has current sum minus s, then we also increment the counter. Fun path. I feel that this counter is getting increment too much. Increment counter and not return anything. What if I just return 1? Because counter is gonna equal to this increment. Return 1. Return 1. No, because no. Because after this is ended, we want to continue to loop this. If I return predominantly, that means if we find this, that is immediately gonna return. It's not gonna go to the next one. Why is it so hard? Why is the recursion so hard? Prefix sum, let's understand that what prefix sum is. For a given array, prefix sum is another array where each element is cumulative sum of corresponding elements in the given array and all its previous elements. Array input prefix sum is equal to A1 is equal to A0 plus A1. A2 is gonna A all these three together. A3 is gonna all these four together. So prefix sum is gonna be like this. Okay, I have that. Now let's say we want to find all the subarray or given array with a target sum. Let's say our target sum is 7 and we want to find all the subarrays of the array mentioned above. And we can clearly see that there are two such subarrays, 1, 6 and 2, 5. How can we utilize the prefix sum to find these subarrays efficiently? There are two ways the prefix sum can help us, since each element of prefix sum array contains a cumulative sum of current and previous elements. Therefore, whenever we see our target sum, we have found our target subarray. For example, since the second element of the prefix sum is 7, therefore a large subarray will form from the start of the array until the second element. Secondly, the prefix sum can also help us find a target subarray that's not starting from the first index. If we subtract the target sum from any element from the subarray, the result will give us the target subarray. So in this case, we have a 2, and the prefix is 9. So 9 minus 7. In this case, 9 minus 7 will 2 and 5. If we subtract the target sum from any element of the previous array, the result will also give us our target sum. For example, take the fourth element of the prefix sum and subtract the target sum from it. Is result 7, yeah? Then it is the second element. This means sum from the third element. Oh. If map has this minus this, wouldn't that be current sum minus s is equal to s? Then we increment counter. Current sum minus s. Is 7 present in the prefix array? Yes. Is the second element. How are we looking for prefix? So 9 minus 7 is 2, but it's not in the prefix. So 14 minus 7 is 7 is in the prefix. Now we can consider each path as an array and calculate its prefix sum to find a required subpath in the above tree. The highlighted subpath are exactly the same as our previous array example. Here's our new algorithm looks like. You have a new map. You have a target sum which is 0. I mean current path sum is 0. Yeah. You have a path counter, you increment current sum. If it's equal, then you increment. If map has this minus target sum, path counter is equal to map.get. Oh, because they could have multiples. Right now I'm just increment by 1, but they could have multiples. Multiple target sum that does that. And then math.set. You set this current sum plus 1 or you add a 1. Then you increment the path counter, increment that counter, and reset this math. Okay. If no is no, return 0. The problem is, like, isn't current sum always getting... Isn't current path sum always gets larger and larger? Okay, this is the most deep nested. After this deep nested is finished, you pop out the current sum from the map. You go to the previous nested sum. The previous nested sum, the current path will be the previous value. No, the current path will still be the nested sum value. Because we are passing in like this. Oh, that's why they pass at 0? Oh, so they don't have a value that tracks this. So there's no top layer value. So this will, after this goes back up, this will get reset. Okay. So my issue is I have a current sum. I have a current sum that maps here, which gets reset. Run this. Okay. So in my case, it's the current sum keeps increasing. And also here, instead of counter plus plus, counter is gonna equal to map.get current sum. Run again. Submit. 14. counter is 0. Current sum equal to root dot value. If rule is null, return 0. We set this value. Oh, before setting. We set that last. So we want to increment this first. If we set this right now, if we set this right now, this is like 1 extra value. Run again. Submit. No. Why is it no? Map.get current sum. If map has the current... If map has this value, okay, if map has this value. Yay! Oh my god! Because it was trying to get the current sum before. It was trying to get this without minus s. But this is before this gets set. So current sum is like, you haven't get to the current sum. Because there's no math.get current sum. Because this is looking for math has current sum minus s. But this current sound hasn't been set yet. It only gets set here. So if we get current sound, this is gonna equal to undefined. So counter plus undefined, that will give us no. That was where the no is coming from. Why is this so hard? Okay, I think it's time for a break. I'm gonna try to do the remaining questions myself. And I'm going to schedule for a... Well, this is a new Master Tool update, so let's play some games in a bit. I'm gonna schedule that, and we'll see you guys next time. Bye bye. I mean, see you guys later. Bye bye. 雅思族破门而开之间谦虚半步，一人曾去目，孤行伫立待的日月当正中，等教问句残花湖，第一口难辨是非，唯有墨鱼之术，盘中人杰的正业户，耳鬓闻琴上风骨。